We are going to look at this triangle, which is isosceles. It has these two sides marked as congruent, and it's also 90 degrees here in the corner. Because this is an isosceles right triangle, we know by the Isosceles Triangle Theorem that the angles opposite the congruent sides are going to be congruent to each other. So this side, this angle, and this angle are congruent to each other. Because of the triangle angle sum theorem informing us that there is 180 degrees total for the interior angle sums, we know that we can find these two angles. One of the angles is 90. 180 minus 90 is 90. Each of these has to be the same angle, so we take 90 and divide it by 2 and get 45 for each of these angles. Now we know the interior angles. We know each angle in the interior of the triangle. We can also know something more. We can know something about the relationship of the sides. And that relationship we will call the theorem the 45-45-90 Special Triangle Theorem. First of all, before we get to the statement of the actual theorem, we are going to experiment a little bit. Let's assume that this side is 1 unit. We also will know that this side is going to be 1 unit since those sides are congruent. This is an isosceles triangle. Since it's a right triangle, we know we can use the Pythagorean theorem. So I'm going to insert my base and my altitude into the Pythagorean theorem and find my hypotenuse measure. Some people attempt to guess that the hypotenuse is going to be 1 also, but that doesn't quite work. When we plug things in, we see that we have 1 squared plus 1 squared equals c squared, the unknown hypotenuse. 1 squared is 1, so we have 1 plus 1 is equal to 2. This value of 2 is c squared. To know what c is actually equal to, we have to take the square root of this. So we find that it's the square root of 2. So the hypotenuse for our isosceles triangle, where the sides here are 1, will give us a hypotenuse of the square root of 2. You can experiment a little with this, choose other values here, and find what the hypotenuse is. What you find is whatever length that you choose for this side, positive real number, that the hypotenuse will be whatever the side length is times the square root of 2, and that brings us to the theorem itself. So for this theorem, if we know that we have a 45-45-90 right triangle, we are calling this the special right triangle. Whatever the side length is here will also be the side length here, and then the hypotenuse will be whatever that side length is times the square root of 2. When we know this, and we know that we have these conditions for a triangle, we can do some problem solving without having to revert back to or consider the Pythagorean theorem. It's built into this diagram. Given a triangle where we know we have an isosceles triangle that's also a right triangle, and we know that one of the sides has a measure of 5, and we are labeling this hypotenuse as c, we are given the directions find the measure of c. To do this, we are going to refer back to our theorem. The measure of c will be whatever this length is times the square root of 2. So without any further calculations, we can simply state that this will be 5 square root 2. This is known as an exact solution. If you type this into a lot of calculators, you will get a decimal equivalent to this. This decimal equivalent that you get out of many calculators is known as an approximate solution. This is an approximate solution because at some point your calculator is giving up in producing numbers. If you should try to do this by hand at some point, you would probably give up as well. This is an irrational number. This doesn't self-terminate. There's no pattern, and there's no fraction representation for this. So at some point, you or your calculator or computer or whatever you're using gives up. So this is an exact solution where we do this very symbolically. If we try to have a decimal equivalent, well then at some point we have to stop or round. Let's try one more problem. We again have an isosceles right triangle, and we are told what the hypotenuse is this time, and we want to find the altitude A. So we want to find this side. Referring back to our diagram here, we see that if we know what the hypotenuse is, then we should divide the hypotenuse by square root of 2 to find out what the altitude is. Now in this case, we have a nice natural number here. If we divide this by the square root of 2, we are going to get either something that we have to have a symbolic representation for, or again, we are going to have this decimal expansion. So taking 8 and dividing by the square root of 2, in many cases you will be asked to rationalize the denominator. So if this is your fraction, we rationalize the denominator. To rationalize the denominator, we're going to multiply the denominator and the numerator by square root of 2. This provides an equivalent fraction because multiplying by the same numerator and denominator is the same as multiplying by 1. So we end up with 8 times the square root of 2 in the numerator, and in the denominator, square root of 2 times square root of 2 is just 2, and this will simplify because we have an even number in the numerator, the 8, and we have 2 in the denominator, so this will factor out a 2, and we are left with 4 square root of 2 to be the altitude here. If you needed a decimal equivalent for this, you could type it into your calculator. I want to point out, I don't want there to be confusion here. Notice that in the theorem we have the hypotenuse has the square root of 2 attached to it. The hypotenuse here does not have the square root of 2 attached to it. If we go from this side to the hypotenuse like we did in the last problem, we see we move from here to here, we multiply by the square root of 2. If we take this side, which is 4 square root of 2, and we multiply by the square root of 2, we get 4 square root of 2 times square root of 2. The two square roots of 2 just multiply together to give us 2. So we have 4 times 2, which is 8, and that is in fact our hypotenuse. So even though we see the 4 square root 2 showing up here, that doesn't mean that we've done something wrong, and it doesn't mean that this theorem is guaranteeing that the square root of 2 term is exactly showing up where you see it here. There is a factor of square root of 2 here, and that's affecting getting a square root of 2 here. So this is not saying that there's always going to be something that looks like the square root of 2 is hanging on to it. The 8 has that factor of square root of 2 in there, but it's kind of hidden because of the length of this one being 4 times the square root of 2. So hopefully that's a little bit of clarification so that you don't always think there's a whole number, and then irrational number here. When in this example, we start out with an irrational term here, and we get a natural number for the hypotenuse. Cheerful calculations.